Okay, it is Monday, April 6th, and we are ready for science. I am turning my page to page 220. We are still in chapter 9. Last week we started talking about the properties of sound waves, and we talked about them being a little bit like a slinky. And we used some terms called compression and rarefaction. When they spread out a little bit more, that's the rarefaction. Um, and we talked about sound being a vibration that can be heard. Sound is a vibration that can be heard. And you should have answered the first side of your study guide page, page 147. And today we're going to look at the back side, page 148. So this should be torn out in your book. This is the one you had the other day that has the slinky on it, okay? But we're just looking at the back. So 12 through 20 are just figuring out if those statements are true or false, and changing the underlined word if it's false. Okay, so we're going to look at the next two pages together. We're going to finish this section up together, and then I want you to go back and see what you can answer. You can even pause me right now, look over your questions, see what it is that you need to know so that you can be listening for those answers. You may need to go back to the pages that we looked at on Friday to see what you can answer from that. Okay, so let's look at 220 and 221 together. Frequency and speed. We need to, by the end of this lesson, we're going to know the difference between frequency and speed. Okay? Sound waves cannot be seen, but they can be measured. The distance from one compression to the next is called a wavelength. And we did introduce that idea on Friday, didn't we? I showed you this picture, and I said that from one compression to the next, that whole part there is called a wavelength. Different sound waves have different wavelengths. These lengths are determined by how quickly the source of the sound vibrates. Sounds that vibrate quickly have short wavelengths. Machines and tools have been developed to help us see pictures of sound waves. So we're not actually seeing them, but we're seeing what the waves look like, how long they last. An oscilloscope uses a type of microphone to convert mechanical sound waves into electrical impulses. Remember that a mechanical wave is one that needs matter, right? We saw that last time. A mechanical wave must have matter to travel through. So the machine that we use to be able to see those waves is called an oscilloscope. Listen again, oscilloscope. Say it with me, oscilloscope. You got it. Okay, the impulses are shown as a wavy line on a graph. The number of sound waves per second produced by a vibration can vary. So are they all the same? No. As the number of waves changes, so does the frequency of the sound. Frequency is the number of waves that pass a point in 1 second. Frequency is measured in a unit called hertz. So when I want to measure frequency of a sound, I measure it in hertz. That's the measurement. Now, frequency is how many times it passes a point. Okay, it's not speed, it's frequency. So if I sit at a bridge and I count cars, okay, 1, 2, 3, that's the frequency, okay? How many are passing a certain point. Sound waves travel in all directions away from the source of sound. That's important. So right now, I am a source of sound. Where are my sound waves going? Away from me, right? Now they're going in lots of different directions. It's going this way, it's going this way, but it's not coming this way. It's going away from us, from the sound. A sound wave can also travel through different types of matter. The siren of an ambulance can be heard whether you are in a house, in a tree, or underwater in a pool. So I want you to think about that in a minute. If you've ever been swimming or you've ever been down in the bathtub where your ears were below the water, what does sound like when you are underwater? Is it clear or less clear than when you're up? It's less clear, isn't it? It's very muffled and it's hard to hear. Because, why? Because those sound waves are having to go through water to get to you. Sound waves move at different speeds in different types of matter, though. The density, or how close the matter molecules are, affects how quickly the vibrations move from one particle to the next. Now that makes sense. When we talked about states of matter, a solid, the particles are packed really tight, close, right? So if I hit on something that's a solid, like this table, that particle is bumping, so the sound can travel more quickly through it. If the particles are spread out farther, then it's going to have to do more work to travel. Do you get it? Because it's traveling through those particles. Of the three states of matter, gas is the least dense. It's spread out. So sound moves the slowest through gases. The sound energy cannot easily move from particle to particle. Also, some of the energy gets used up as it travels through the spaces between the particles. This slows the movement of the waves, so it doesn't move as fast as if it's going through a sound. Or going through a solid, it's going a little bit slower because it's having to go from particle to particle and they're spread out. Air is the most common type of matter through which we hear sounds. That should be something you hang on to, isn't it, in your mind. The speed of sound in air is about 335 meters or 1,100 feet per second. This is how fast sound travels through the air under specific atmospheric conditions. In different conditions, such as a hotter day, the speed of sound will be different. That's interesting, isn't it? The particles in liquids are denser than the particles in glasses, so sound moves more quickly through liquids than it can through gases. The waves also travel farther than they can in a gas. Solids are the densest state of matter. Their particles are very close together. The sound waves easily move from one particle to the next. So sound waves can also travel faster and farther in a solid than in a liquid or a gas. The speed of sound is not the same as the frequency of sound vibrations. Speed tells how fast something is moving. Okay, so here's the difference. Speed tells how fast an object is moving. Frequency tells how many times it passes that same point. Okay? So think of watching cars traveling on a straight highway. Suppose all the cars on this highway are traveling at 50 kilometers per hour. That is the speed of the cars, 50 kilometers. However, the frequency of the cars is the number of cars that pass you in a set period of time. So they're all going 50 miles an hour, 50 kilometers per hour, but how many pass me is the frequency. Frequency is how often they pass. In the first minute, perhaps only one car passes. In the next minute, 5 cars may pass. The speed of the cars stayed the same, but the frequency changed. The speed and frequency of sound waves are related in much the same way as the speed and frequency of the cars on a highway are related. Okay? Now, to understand this idea a little bit more, I want to look at 21 and 22 with you. You're going to go back and do 12 through 20. 21 says, in a half hour, 5 cars passed over a bridge. In the next half hour, 12 cars passed over the bridge. All of the cars were traveling the speed limit. What changed? The speed, the matter, or the frequency? So what changed? First it was 5, now it's 12. Frequency, right. Not speed, they're all going the same, and nothing changed about the matter. They're still going in the same way, okay? Now look at 22. The cars on the dry pavement are traveling 50 kilometers an hour. But when the storm began and the road became icy, the cars slowed to 30 kilometers per hour. What changed? Speed, direction of travel, or the frequency? So it was 50 kilometers per hour, now it's 30 kilometers per hour, what changed? Speed, you're right. Okay, so do you see the difference between frequency and speed? I think you do. Okay, 12 through 20. And then in the comments, I want you to think of a sound, okay, any sound, and I want you to tell me that sound waves are moving away from what sound? Okay, so for example, my sentence would say, the sound waves moved away as Mrs. Barnett talked. Okay, so everybody's sentence can start with, the sound waves moved away, but then I need you to tell me from what sound. Okay, so the sound waves moved away from Mrs. Barnett as she was speaking. Now you tell me something different. The sound waves moved away from the bird as it chirped. Okay, I just gave you two. You got to give me one now, okay? The sound waves moved away from, you fill in the blank.